All right, so we started with the plotting that part, and then comment on the correlation. What are we thinking for correlation today? So definitely positive.
Moderate and linear.
Moderate and linear, okay. Yeah. Anyone else? I almost feel like it's almost a strong correlation. The only reason I say strong rather than moderate is just because there aren't any like big like outlier points. That's kind of how I look at it. Okay. So yeah, so moderate, I would almost say strong and positive, but just because I don't see any like major outliers that are going to be swaying it towards the moderate, that's the only reason I would say that. But yeah, strong, positive, and linear. Okay, and then the next question says, why is it appropriate to find the line of regression, or the regression line of y on x? And that's appropriate because we have a strong correlation, actually. That's how I would tell it's a strong correlation as well, when the book hints me to it. All right. And then part C says, find the line of regression of y equals x and draw it on the scatter diagram. I drew a second diagram so we could draw it down there, but we could just draw it on the first one. I think it's fine. I'm going to change colors so we can find that one. So the first thing we want to do is we want to find the mean of our x values, the mean of our y values, and we'll find that center point. Or we could just type it all into our calculator and find that line of regression. All right. So, okay, so, you looked up the R value, the Pearson correlation coefficient. That's smart, because that tells us the R value is 0.85, and that tells us it's definitely a strong correlation. That's perfect. Okay. So yeah, finding the line of regression. What do we end up getting for it? Is anyone able to put it in their calculator and calculate that? It would take a minute.
0.15 for A, and then 11.99, so I just did 12.
Okay. We'll just say 12.0 so we know we rounded it. All right, so whenever we round something up, I would just use that 12.0. All right, so we have a line, 0.15x plus 12. All right. And what that's telling us is basically if it's 0.15, what is it? We're going like up 1 over 0.15, is that right? Yeah, that's kind of annoying to try and sketch that perfectly here. Let's see. So we are going to say this starts probably right around here. And the slope is not going to be great. Probably something like that for our line of regression. And then part D asks, estimate the shoe size of a student who is 163 centimeters tall. 163. So we could say 37 and a half. Okay. Would be the shoe size. Okay, and then explain why it is not reliable to use the line of regression on y of x to estimate the shoe size of a student who is 150 centimeters tall.
Wait, we also need to explain why it's a valid process.
Oh, okay, sorry. So it's a valid process, we would say, because basically what the last two questions are hinting at is the next question is hinting at is that 150 is outside of our data set. The minimum value on this entire data set is, where is it? I think it's 160. So if you start evaluating something that's at 150, it's outside of our data set, so we don't know if there's going to be a change in how shoe sizes fit when you get a little shorter, right? Because somebody that's 4 feet 11 inches, like if we're talking about US shoe sizes, right? And the average woman's shoe size is like, let's say size 7 or size 8. But someone that's really short, like 4'11" or something like that is not necessarily going to have a size 3 shoe. They're still going to have like decent sized feet. So the big thing is it's not reliable to use the line of regression outside our data set. Versus part D, you can say it's reliable because it falls on our line of regression in the data set. Okay. All right, and then explain why it is not appropriate to use the regression line of y on x to estimate the height of a student whose shoe size is 38. All right, so this one's weird because like 38 should fall in the data set, right? Like 38 is right here, but this is saying it's not appropriate to do that. Anyone know why? Think about our variables here, right? One of these variables is independent, one of them is dependent. Which one's the dependent variable here?
Shoe size.
The shoe size. So the problem here is you can't use your dependent variable to determine the independent factor. You can't work backwards like that. So that's the key for this last one. We can't use our dependent variable like that. So that's kind of the key for this particular part of the problem. We don't want to use the dependent variable to determine the heights of people, or the shoe size to determine the heights of people. So I'm just curious because these are European shoe sizes here. I don't know what the translation is for from American sizes to European sizes, but I do know that Shaq wears a size 23.5 US sneaker. So I'm curious, what size would that be in European?
Well, 37 is a women's 8.
37 is a women's 8. There you go. So this is a women's 8. So Shaq would be like probably in the 60s on here. I'm not sure. He's 23.5 American is his size. I mean, that's insane. So yeah. Okay, so let's move on. Now, this is really weird, but for some reason your textbook decides to introduce piecewise functions, which just, I guess this is as good a time as any to talk about piecewise functions, but it's in chapter 6, which makes me think it's important on the IB exam. So a piecewise function is...
Also update, his shoe size is a 47 European.
47 European. It's got to be bigger than that. That doesn't sound right. Could it really be 47 only?
Well, his US shoe size is 14 and the UK is 22.5.
No. His US shoe size is like 23. That's not right. The 14. I'm a size 13 and Shaq's like 2 feet taller than me. Let's be honest here. All right. So a piecewise function is a function whose graph is made up of several linear segments. This is a piecewise linear function, I should say. All right, that's what a piecewise function is. Okay, so a function whose graph is made up of several linear segments. All right, so whenever we're looking at a piecewise function, like this example down here, it's giving us two equations here. It's saying, hey, we're starting with this first one. And it gives us a little domain there. It says, hey, as when x is between -2 and 3, that's where our piecewise function falls. And then it gives us a second one and says, hey, we're going to follow this equation from 3 to 7. Okay. So what this looks like then is just saying, okay, well, f of x equals 4 as long as we're in this range. Well, I'm going to do this. I'm going to do this in blue, sorry. Stick with the color coding. As long as x is between these numbers, then it's always going to equal 4. And then the second equation, we're going to use -x plus 7 as our linear equation, as long as x is past 3, not including 3, because 3 can only be included once, and 3 is being included right here. So this is not including 3. So that's important to notice right there. If it's including 3, then you don't have a function anymore because it's being included in 2 different spots on the graph. Okay. So the first thing I had to ask myself is, let's find f of 0. And we got to find out where does 0 fall on the number line. So f of 0, that's going to fall in to this one. So we'd plug it into this equation then. So f of 0 equals 4. Done. That's a nice easy one. And then f of 6, that's going to fall into the green equation. We're going to do different color. F of 6, that's the green equation right there. So we would plug it into that equation. That's how we use piecewise functions. We have to determine which domain we're using, and then we can plug in that number and figure it out. So in this case, f of 6 equals 1. And then if you're ever asked to state the domain of a piecewise function, the domain is just going to be the whole thing. So -2 is included. You guys might remember this interval notation from last year, and it goes all the way to 7, and 7 is included. So that's interval notation. And then the other way we could have included it was -2 is less than or equal to x, less than or equal to 7. Do that in a different color. And that is set notation. Either one is perfectly fine. We talked about both types last year in class. You can use either one to describe your domain. All right, whenever we're talking about domains. But that's how you do it for piecewise functions. Okay. Last part, plot a graph. So I'm going to go ahead and say, let's do this. So for this one, we're going to say, we'll start with the blue equation. It's just going to be 4 from -2 to 3. Oops, I'm going to do this a little better. Okay. -2, -1, 1, 2, 3, 4, 5, 6, 7. All right. So it's going to be 4 from -2 to 7. I'll draw that line there. Or -2 to 3. And I guess I forgot to put the scale up here. 1, 2, 3, 4. And then if we need to go negative, we'll go negative. And then from that point on, it's going to be -x plus 1. But we want to check our first point. So what's happening at 3, if I actually plugged in 3 here, I'd get -3 plus 7. That does indeed equal 4, so that's kind of nice. It will start there. but it'll be an open circle at 3 instead of the closed circle. I'm going to do it in a different color. And then the slope's going to be -1. So it's going to go 4 and 3, 5 and 2, 6 and 1, 7 and 0. And that's it. And that would be my piecewise function. Okay, that's how I would sketch this one. They might be disjointed. They don't have to be connected. Like right now, they're connected at the point 3, 4. But the piecewise could jump and skip somewhere else. All right, and that's why the open circle and the closed circle is very important. But that's in general what piecewise functions look like. Let me zoom out just a little bit. All right, so the last thing I have today, I just have this little investigation that I want you guys to work on. I could send you to breakout groups, or I could just keep it as a big group if you're going to work on it individually anyway. I feel like, do you guys actually talk in your breakout rooms, or do you just sit there? Just sit there? Yeah, that's my fear of breakout rooms, since I feel like they're not used properly. Anyway, so yeah, just go ahead and work on this problem then. We'll go over it in just a couple minutes to just kind of think about them. But basically, this is what the last section is in our textbook, is just interpreting the regression line. So what's the line telling us in a real-world context? Okay, so you can probably expect something like this on our assessment next week when I'm just asking you, what is this one telling us exactly? So problem A, I highlighted in blue, this it's how many hours per week a student spends on social media. I guess I could highlight that part too. And then B versus Y, which is sleeping. So if we were trying to put this in context, what's the slope telling us about this equation? First of all, what's the slope of the equation going to be? It's right there, right? It's going to be this -2. Okay. So think about, what's that 50 representing? Let's start with that part. Anyone think they know what the 50 is?
That's the max hours.
Yeah, exactly. That's the number of hours you're sleeping, right? So 50 hours a week, which I was thinking 7 nights a week. That's not great. I don't think, right? I don't know.
That's 2.25 days.
Yeah. Well, yeah. I don't know. What I'm trying to think. Well, because you think about 7 days a week, right? And you're sleeping 8 hours a day. That would be 56, right? So 50 hours is less than 8 hours of sleep already, which is not good. You guys need more sleep than that. High school kids are actually supposed to get about 9 hours of sleep a night, theoretically. I'm sure when you get to adulthood, you can actually do better with it. You'll be fine with 8, but in high school, you're still supposed to get more sleep. Anyway, let's take a look, though. Let's go out. All right, so this is saying we start with 50 hours of sleep, and so what's the slope telling us then? If I plug in a 1 here, I'm on social media for 1 hour, what happens to my sleep?
It decreases.
Yeah, by how much? Every hour I am on social media.
By 2.
Yeah. I lose 2 hours of sleep. And this is basically saying that our baseline's kind of like, if I'm not on social media at all, I start with 50 hours of sleep. That's how much I sleep every week. Okay, that's kind of what part A is telling us. Would be this first one. Okay. Part B, we'll do this one in red. All right, this one's telling us about age, how old a kid is, and their hand length in centimeters. So what's this one telling us? What's the slope telling us? How fast are my hands growing? (1.7 centimeters every year. Every year they're growing 1.7 centimeters. Now, conceptually, like, how long is this linear curve for like hand growing? How long is that going to last, right? Are my hands still growing 1.7 centimeters when I'm 35 years old? Probably not, right? Otherwise, I would have massive hands by this age. So there is a point when it stops, right? My hands probably stopped growing when I was 20, you know? So there's just something to think about there. So these regression lines, they're going to have limits to when they work and when they don't work. Like same with the sleeping one, right? You lose 2 hours of sleep, but let's say you spend 25 hours on social media in a week, which is entirely possible. Then technically by this model, you're getting zero hours of sleep a week. If you spend 26 hours on social media, now you're getting negative 2 hours of sleep, which doesn't make sense anymore. So these models do break down, and it's up to us to determine when they do break down. That's where your interpretation of the data is super, super important. Okay? So that's conceptually what we're trying to get at from this information here. So when can the gradient of the regression line tell us about the correlation? What can it tell us about the correlation? So this is, it can tell us like pretty much like what's the ratio of X to Y. So on part A, we're saying every hour I spend on social media is kind of impacting by 2 hours my sleep. All right. Part B, for example, it's weird because my hand starts at 1.5 centimeters and then it more than doubles in size after 1 year to 3.2 centimeters, right? So that part B is kind of a weird one, and that's where we can explain the y-intercept might not always fit or might not always be relevant in a given context either. So just important to notice those things about interpreting the data. All right, so pretty short lesson today. That covers everything we need to know.